Hello, guys. Hello. Okay, thank you very much for coming. So I work for Nvidia, and I work with a lot of software vendors who deploy or develop deep learning solutions for different applications. So deep learning is a new technology which evolved in the last few years only. In the IT industry, we have waves of innovation. We had mainframes in the 70s, then minis in the 80s, and the PCs in the 90s, then internet. The latest evolution we have is AI revolution, and deep learning is a big part of it. So this revolution started only a few years ago. There was a paper in 2010 by Alex Kryzewski, Ilya Susketer, and Geoffrey Hinton, which demonstrated how to achieve better image recognition using deep learning than traditional machine learning methods. And this particular paper and this particular results just blown everybody else out of the water. And the reason is all of the work prior to that particular day was done using traditional machine learning methods where people look images, they construct feature vectors, they do tons of work on feature engineering. Literally, people spend their entire careers, 20, 30 years, doing feature engineers trying to recognize the image. And then this particular approach, there was no feature engineering at all. So the model itself was able to recognize what's in the picture, and you never told the model what to look for. So that was the first results, and they developed better results than everybody else had in the industry. And since then, the entire computer vision industry switched to deep learning, and nobody else does anything else, because everything else is a superior approach. So all of it, of course, is run on GPU. Since 2012, we had several developments. First, Andrew Ng and his group developed a way to develop scalable solutions based on GPU, and they did it in 2012. So this paper is actually 2013. You can look it up and see how people were able to distribute the workload and deliver, solve complex models on a GPU, on a cluster of GPU. In 2015, so the slide in the middle is a very important one. So when you do feature engineering and you do image recognition, at some point you stop improving significantly. You kind of you try to capture every particular edge case and et cetera, et cetera. At some point, your model just stops improving. In deep learning, there is no that kind of barrier. So in deep learning model, so for example, in a traditional machine learning model, let's say you train a model to recognize human face. So, but then picture changes. Let's say you don't have two eyes. If you have a picture like this, as a human, you still see human face. But machine algorithms stop working. Machine learning algorithms stop working because one of the eyes is missing from the picture. In machine learning approach, there is no limitations like that. So all you need to do is give the computer more images, more processing power, deeper network. What deep means multi-layered. Add more layers, and it will continue to improve. So what you see with deep learning results is, with machine learning results, you kind of reach a limit. With deep learning, you continue to improve and improve and improve. So right now, deep learning are able to understand images better than humans do. So about a year ago, the computer models start labeling the images better than average humans. And the last slide looks at the speech recognition. And the speech recognition is the same. At some point, as you improve the model, the computer models become better at understanding human speech than humans do. Okay, so as a result of this type of achievements, we have tons of deep learning implementations everywhere. The first chart is deep learning models at Google. Google made massive investments in this area, and right now they have more than 2,000 different projects started at Google to apply deep learning to particular things. They apply it to everything that moves, right? In the middle, it's deep learning frameworks. Most of them been open sourced. You can go and download it from GitHub. So those are the main frameworks that people use right now. But if you would like to know how many frameworks out there, the last counts we have is like 67. So the innovation continues. People create their own approaches, they write their own frameworks, and it continues to grow. And the last slide is the number of companies involved, engaged with Nvidia on different deep learning projects. And 2013, we had 100, and it was a big achievement. Now, last year, we had 3,400, so that's kind of the trends that we see. So this is, again, talking a little bit more about why deep learning works. So if you have, if you keep adding more data, you have a bigger, which means deeper model, which allows you to do more nuanced decision making, and more computation, you get better results. So in this particular case, Microsoft went from 8 layers for image recognition to 152 layers, so more nuanced models. And they added additional GPU capacity. They increased the performance from 16% error rate to 3.5, right? And the second example, so it's a 16 times bigger model, gives you several times better results. And the speech recognition example from Baidu on the right is very similar. So it's a larger data sample. They went from 7,000 hours to 12, and a larger GPU cluster, and they were able to get better results in terms of the error in speech recognition. So how does this work? So in deep learning world, there are 2 stages. There is training and there is inference. When you train the model, it's a very computationally intensive task. You have a GPU cluster, and you recalculate those parameters over and over again. You have millions of neurons and recalculate them thousands of times until the model converge to the good results. And we see applications everywhere. So one of the applications is the satellite images. So in this particular case, this is a NASA project called Deep something, I forgot. So what they did is they look at the satellite images and try to train the system to recognize carbon impact. So if you have around big cities or whatever, you can actually see where the carbons are accumulated. Other people use it, the same technology for other purposes. For example, I know one of the Wall Street companies, they look at the number of cars at the parking lot, and if the number of cars in the parking lot of the store declines, then they sell the stock, and if it's growing, then they buy the stock. So you can do something very practical with it as well. The middle example is from Pinterest. So what they do is they look at a similar pins, and if you have a similar pins, then you can recommend something to purchase, or you can suggest people what to look at, right? Very much a similarity search. And the last example is a company which used deep learning on tractors to recognize what needs to be sprayed. So right now, when the tractor goes around and sprays pesticide on lettuce, it sprays everywhere when it's needed or not. So if you can actually see where the weeds are, apparently you can reduce the pesticides by 90%. So you save 90% of the cost on pesticides, plus the consumer get 10 times healthier lettuce because it's not sprayed with crap, 24/7. One of the big examples for deep learning is healthcare. So healthcare is one of the industry which you wouldn't expect to be early adopters, but in case of deep learning, it's taking off. The first example is Mount Sinai Hospital. So what they do is they look at the electronic health records, and this particular sample was 700,000 patients. And if you look at the electronic health records, apparently you can see when the particular disease is approaching, right? It's like, if your test results start changing over time, and so you can predict when you're going to have a chronic conditions a couple years from now. And it's just math, right? You can predict those things. But in the current healthcare system, when you have, doctor only see you occasionally and he doesn't have the time to look at your history, this data is not being utilized. With deep learning model, you can look through this 700,000 patients with, tons of different results and predict where the problems are. The second result is pathology. So just looking at the images and look where the problem is. I think this was a prostate cancer from a US Naval Hospital. So this is image problem. So the computer can look at the images and see whether there is a problem there or not. And the last one is the example from Massachusetts General for radiology. What they did is they look at the images of bones and see if the child has a problem with growth, development, etc. So looking at the bone density. So we talk about training. So when you train the model, you need to have a lot of computational capacity, and then there is inference. So once the model is trained to recognize a particular thing, you train, it can be used, applied to predict or to recognize the same problem when it's visible again. In many cases, it's done in a data center. In this particular example, Aristo is a company which applies artistic style to your own photo. So you upload your own photo or video, and it will change it to make it more interesting. So this type of processing is done at the data center. So we have a lot of companies using deep learning. Obviously, a lot of companies you already know have deep learning used for at least one application. And of course, in many typical companies, you might have dozens or hundred potential applications, as a Google example indicated. We also have a lot of startups. The last count, we have about 1,500 startups in our early adopter program called Inception. And for example, Deep Instinct is a company which is using deep learning for malware detection. So that's a standard antivirus stuff that you guys are all familiar with. So deep learning is better at detecting malware because it's more able to capture mutations. The malware keeps mutating. And if it's exactly the same file, you can capture it, but it changes a few lines of code. Suddenly it looks different. You might miss it. So deep learning is better at capturing mutation. In addition, it's able to capture the threats which are not known yet. So, and there are different ways to do it. So deep learning can be applied to looking at actual bits. You can look at the behavior of the code, or you can look at the metadata. It's like where it came from, what it's called, the file size, all those kind of things. So there are 3 different particular models that can be applied. And so the malware might become a solvable problem. So you don't get viruses on your PC once all this work is completed. So Deep Instinct is a startup which started working on this problem a few years ago. We now have quite a few companies trying to do the same. Now, it's a significant amount of work. So when you start working with deep learning and you just do the first implementation, you get okay results, maybe 60, 70% detection. And then you start developing your model, adding additional intelligence, and getting more nuanced. And you can get 98, 99% detection of the known threats. Of course, detecting unknown threats is even more interesting. So the genomics is a great example for deep learning applications because you have massive amount of data. The data is very simple in nature, but the amount of data is so huge that it's very difficult to process it. So the question is, how do you find patterns in the data and predict particular things? So it's used in many different, there are many different genomics companies who use deep learning to predict outcome of trials. Personalization medicine is coming at some point. Who should be treated with what particular disease and etc. For self-driving cars, so it's a big business for us. So if you listen to what Fords and GM saying, they're like, in 3 years, every car is going to be a self-driving car, which is kind of difficult to believe. But all of them are making massive investments. So the biggest problem with self-car is perception problem, which is the problem we're solving. So the car needs to be able to look at the streets and within milliseconds recognize if there is a tree in front of it or not, right? Should I stop or should continue going? So it's a mostly perception problem. So we're working with every single large car manufacturer to implement those systems. And those systems will probably be implemented in stages because there are 5 different ways, 5 different degrees to which you allow computer to drive for you. But eventually within a generation or something, if you can think about the next generation, will not know how to drive at all. Because the technology will be able to do it better than the humans can. Okay. And the last example is a Prisma. It's another example of a company which used deep learning to apply artistic style to your own pictures. And it's a company which went public in the US about 3 months ago, and it's was exploding like crazy. So it's another example of deep learning application. So we talk about training. We talk about inference done in a data center, and then finally device. So the car is device for us. So car is a device, and on the device you need to be able to quickly make a decision, whether go, stop, left, right, whatever it needs to be done. So you need to collect all the information from the sensors, quickly run deep learning, continuously run deep learning inference, and make decisions whether to go forward or not. We also have other types of devices. So people building deep learning into the consumer cameras, so you actually can understand things. Like simple example, like if you're in a company like Twitter, you don't want people, if when somebody swiped a card, you want that person to come in, but not other people come in with him. So like recognize who is coming in, or maybe you don't need to swipe anything. The camera will recognize who you are and let you in and not allow other people in. So this is a lot of application and basically recognizing people, faces, using cameras. You see a lot of devices from Google, Alexa, from Amazon. All of those devices use deep learning to help people manage their homes. Drones, a lot of drones are building small version of GPU into their device in order to make intelligent drones. So the drone doesn't hit every tree, only doesn't hit any, hopefully. The same as a little robot at the end which delivers groceries to people. So it's a small robot, but it needs to know where to go and not to go. It needs to be able to navigate the streets and not hit obstacles, people, or cars, right? So it still needs to have the intelligence capability. So besides deep learning, we also have several analytics applications. So the analytics space keeps evolving. Traditionally, we have a lot of business process companies, and you think about traditional data management, then web, digital, and now we have a massive amount of information, which is its IoT or video, etc. So traditionally, the stack looked like this. And with the deep learning, we have with deep learning and GPUs, we have a lot of companies which are able to take the power of GPU and apply it to solve analytics problems. So in this particular example, we are showing MapD is one of our database vendors. Just a relational database, the same way you access it using JDBC or DBC. But unlike the traditional demos that you'll see from an average vendor, the normal vendor will show 3 days of data. Because MapD runs on GPUs, they show 2 years worth of data. So that's kind of the 2 orders of magnitude improvement in the amount of processing capacity you have. So we have a partnership with Spark. 2 weeks ago, Spark announced availability of GPUs and Spark clusters. So if you go to Spark today, I know you guys are all Scala people, you can click the button and on the GPU and start running your deep learning jobs within Spark on Databricks. So we have tons of applications which are growing rapidly. We have AI as a service provided by several companies. So I don't know if you're familiar with Microsoft, Azure, machine learning, Google doing something similar, IBM Cloud, Amazon AI. There are tons of companies offering machine learning as a service. There are tons of companies using GPU, offering GPU in the cloud if you have your own problems that you want to solve. So all of the big vendors, Azure, Amazon, have GPU clusters available now, within the last few months. And finally, we have analytic capabilities to solve the problem which were not solved before. So that's the end of my presentation. And I think we have a couple of minutes for questions. 1 minute. Okay, so the question was, what are the evil and dangerous applications? So if you, there is one area of deep learning which is called adversarial networks. So if you are in an adversarial situation, for example, if it's a cyber or fraud, so people attacking you, becoming more sophisticated and have a more sophisticated technologies, probably using deep learning, and you want to defend yourself, so you have to develop more sophisticated capabilities also using deep learning. Otherwise, you're going to be left behind. So in adversarial situations like a fraud or cyber, you generally need to have capabilities to defend yourself. But in general, I don't believe in singularity. So I think all of this stuff that we're showing, it's just math, right? It's not like conscious systems that try to take over the world. It's just math, right? So like you have a complex problem, and you have pattern recognition technology which can solve those problems. And suddenly, the machine can see, whether to go or not. So that's a big improvement, but it's not, it's nothing else beyond that. Thank you very much.